explore the biggest questions of our time, and get to know the people behind the science. This is Curiosity Meets Discovery, research talks from inside the Max Planck Society.
Hello everyone, and welcome to Curiosity Meets Discovery. Today, we're exploring the topic of climate change, an important issue that dominates headlines and is shaping international dialogue. While we can't deny the impact it has on our world, have you ever wondered about the science behind climate change? What is actually happening in the atmosphere to cause temperatures to rise? Today's guest is Dr. Bjorn Stevens, director of the Max Planck Institute for Meteorology in Hamburg, Germany. There he heads the Atmosphere in the Earth System department. Bjorn's research strives to understand how water in the atmosphere conditions the behavior of the Earth's climate system, answering questions such as what determines the behavior of clouds and how do clouds impact large-scale atmospheric circulations and influence interactions among other components of the Earth's system. He is particularly interested in new technologies that will benefit researchers who are making predictions on how climate change will directly impact our day-to-day life, and in turn, our health, safety, and the overall well-being of our planet. Welcome, Bjorn, and thank you for sharing your research with us.
Thanks very much, David. It's a real pleasure to join the series today and tell you a little bit about our research on understanding climate and climate change here at the Max Planck Institute for Meteorology in Hamburg. My talk's gonna try to do two things. It's gonna try at the beginning to explain to you what we know and why we're so certain about it, how we got there. And then I'm gonna tell you a little bit about the things that we don't know that we'd like to know and that we think we have a way to know, and see if I can convince you that that might be a good thing to follow. So I'll dive right in, and the way I kind of like to explain this problem is with this figure here. So this is a favorite cartoon character of many people, Obelix, from the Asterix and Obelix series. And I use him to explain how Earth manages its energy budget. Because when we want to understand climate, it's really just a question of understanding flows of energy in and out of the system. And the temperature of the Earth is really what it uses to manage that energy flow. So the image here on the left, I don't know, can you see my cursor? Yeah, so the image here on the left is reflected sunlight, and it's mostly reflected from the surface. And it's reflected from the surface because the atmosphere is more or less transparent, except where we have clouds, the little white blobs all around there. So the Earth gets its energy from the sun, and if it would get energy, it would just increase its temperature and increase its temperature and increase its temperature. So somehow to stabilize the temperature, it has to get rid of the energy. And if you think of this in the sense of Obelix here, it's sort of like he's famous for eating wild boars. So if he just ate wild boars and ate wild boars and ate wild boars and didn't do any exercise like carrying stones around France or chasing Romans, he would just get bigger and bigger and bigger, like the Earth would get warmer and warmer. So the equivalent to the Earth chasing Romans and carrying stones around the French countryside is infrared radiation. So as the Earth heats up, it emits radiation in the thermal infrared. That's wavelengths about 20 times longer than it gets from the sun. And if you looked at the Earth in the infrared, you would look at it kind of like a gaseous planet. The atmosphere, and that's what makes a greenhouse atmosphere, is opaque to a large degree in the thermal infrared. So if we imagine ourselves in space looking down at Earth, we would see a picture that looks like this. We wouldn't see any of the surface features. So like Earth and like Obelix, Earth is a little bit easier to understand in the ways in which it consumes the energy from the sun than in the ways in which it gives it back. So I'm going to take a little bit of a deep dive to try to explain how radiant energy transfer works in the atmosphere and why that leads us to be pretty confident in our understanding of how CO2 causes global warming. So I'll begin here by taking that picture and looking at that in a bit more detail. And here the picture, I'll just explain it to you. It's from a satellite. We're looking at 6.2 microns, that's up here. And we're mostly seeing the emission from water vapor. Now, it turns out that Earth's atmosphere is a gas. And because it's a gas, it's compressing as you put more and more atmosphere above you. So the atmosphere low down is very compressed. Above, it's very expanded. And that leads to the temperature to change with height as well. So the temperature aloft is a lot colder than it is near the surface. And we call that this temperature stratification of the atmosphere. And what that means is that if emission, thermal emission from the Earth is coming from very high in the atmosphere, it's coming from a region that's very cold. And that's white or gray here. And if it's coming from very deep in the atmosphere near the surface, then it's coming from a region which is very warm. And so you have lots of emission. So the color here, the gray scale, is showing you essentially the temperature of emission. And you can think of it as how deep we're seeing into the atmosphere. So when it's dark, we're seeing very deep into the atmosphere, light, not very deep into the atmosphere. And you could ask, why is that? You know, why in some places is it very white here, in other places it's very dark? And that's really controlled by the amount of water vapor. That's the greenhouse gas in this case, which is controlling the emission. And in these very dark regions, there's a dearth, a real absence of water vapor. So the atmosphere is fairly transparent to the infrared radiation, and we can see very deep into it looking from outer space, or the emission comes from very deep in the atmosphere. I'm gonna let this play. This is just days. There's a clock here on the bottom left. These are some days in December in 2013, and it's measurements from a satellite. And you can see it's not the whole globe. It doesn't go to the poles. It's about a 60-degree frame. And you see how the atmosphere moves, and you tend to see this preference of these dark regions to be kind of off center here, about a third of the way up from the center in the top and the bottom, kind of symmetric. And what they are is large regions in the subtropics where the air is descending, and there it's drying. Now you might be beginning to see what we've done is we've essentially shifted the wavelength, and we've made it more transparent so we can see deeper into the atmosphere. And that was done to convey to you the fact that how you look at the atmosphere depends on what wavelength you're looking at. So if you would look at longer wavelengths, then you wouldn't see as much of the water vapor because it's not so absorbing, and you'd be able to see deeper into the atmosphere and almost to the surface. Here you also see Africa emerging and Brazil on the far left. And you see these really white features that you saw before are clouds. And they pop up during the day like here, and then they go away during the night. So you're seeing the daily cycle of the clouds. But you're seeing the swirling motions of the atmosphere, how it regulates its concentration of its most important greenhouse gas, which is water vapor, and how that influences its ability to transfer radiation back to space. So remember, the job of the surface temperature, that's what the Earth uses to produce, to radiate enough energy to space to balance what it gets from the sun. And if it isn't cooling off fast enough, then it will just warm up from the sun's energy. And if it's cooling off too fast, then it'll cool down and emit less energy. So temperature is what regulates that. So let's look in a bit more detail. And here the dive gets deep. And what I'm showing you is the spectrum of radiation on the right-hand side, and trying to make the point that there's really just two well-separated spectra of radiation. One is visible radiation, and that's emitted like a black body from the sun, and the sun's about 6,000 Kelvin, about 20 times warmer than the Earth. And this would be the Planck black body curve, the blue line here, of radiation coming from the sun. And the red one would be the Planck black body curve of radiation coming from the Earth. And if it's warmer, it shifts to shorter wavelengths, and you actually get more radiation, but here the scale is normalized. So really the sun's black body radiation, which we only intercept a little bit of, is much more than at these colder temperatures here. So by regulating the temperature, you shift how much energy and the wavelengths at which that energy leaves the Earth's atmosphere. Now, if you're an infrared photon at about 10 microns down here, you can leave from the Earth's surface and get out pretty easily. There's not a lot of absorption features at 10 microns, and that's shown here. These are absorption features, so absorption lines. It's the strength at which a molecule absorbs a certain amount of radiation, and they're quantized lines, and there's thousands and thousands and thousands and thousands of water vapor lines, and they're shown here in wavelengths relative to the relevant for the Earth. So if you look here, we call this area around 10 microns the window because there's not many absorption features. So photons that are associated with the energy of, a 10 micrometer wavelength, they can get out pretty easy. But if you happen to be here at say 6.2 microns, not 6.3 right in the gap, but 6.2 right there, you'll have a hard time getting out because of these absorption features. These are the rotational bands of water vapor at 6.3 and 2.7. And these are rotational bands of water vapor. So the water vapor molecule has the H and the two O's, and it can rotate and it can vibrate. And all of these different quantized rotations and vibrations give rise to these bands. And luckily, we have this gap here where energy can escape from the surface. So it's important when we think about how energy leaves Earth's atmosphere to think about what these vapors do, what this window does, and what gases do. So part 2 of the deep dive. This is the same plot I showed before, but it's flipped around. Here, I don't have wavelength, I have wave number. So large wave numbers are short wavelengths, and short wave numbers are large wavelengths. And what I'm showing here is the radiation that's escaping to space. That's this darkened line here. And there's, this is kind of a running average of all these little absorption features. And then the solid smooth lines are the Planck blackbody curves for 2 temperatures. This is if you radiate at a warm temperature, you have lots of radiation at a larger wave number, and a colder temperature is less radiation at a smaller wave number. And what you see is the actual radiation that is going out to space varies between this warm temperature and the cold temperature, depending on where it's emitted. So if we're here, forget about this bump for a second, but if we're here in the middle of the curve around wave number 1,000 inverse centimeters, what we see is that the curve is fairly close to the TS, the warm surface temperatures, which means that's radiation coming from near the surface. It's being emitted at temperatures which are about that of the surface. Whereas when we're over here, the temperature is close to this T-min. It's about 100 Kelvin cooler. So it's temperatures of high in the atmosphere. And what the curve shows you is there's 3 types of emissions happening. There's this emission here, which is what we call the window. That's radiation that comes from near the surface. And on the flanks, water vapor, that's what we saw before, water vapor is controlling the emission. And so depending on how strong the water vapor is, it's at a very low temperature or a more intermediate temperature. But in these regions, the vapor controls the emission. And then we have these 2 features here, and these are gases. And what the gases do is they work like water vapor. Water vapor is also a gas, but I distinguish gas from vapor in the sense that gases aren't controlled by the temperature and the vapors are. So in Earth's atmosphere, it turns out that water vapor is strongly dependent on temperature. And this gives rise to these sort of 3 effects: gases, windows, and vapors. And I've tried to draw this up here for you. And so we're imagining an atmosphere, and we'll talk about the window first. This would be temperature, and this would be altitude. So as you go up, you go higher, and the temperature gets colder, and maybe it goes from 300 Kelvin or, 80 degrees Fahrenheit, 27 degrees Celsius, to 100 Kelvin colder, or 200 degrees Fahrenheit colder. Colder. So the temperature decreases with height. And if you increase the temperature and you radiate from the window, then you just get more radiation because you're radiating from a warmer temperature. So here I imagine here's a current temperature. We warm the planet. It goes to the dashed line. It's a warmer temperature. If emission comes through the window, that means it's not interfered with by the atmosphere, and it comes from the surface and it escapes to space. So here we just get more emission from the window. That's great. So if for whatever reason the sun got brighter and we were getting more energy, or we have more CO2 and we need to get rid of that, we just warm the planet a little bit and we can emit more radiation through the window. The problem is that the window isn't all that big. There's lots of regions out here where there's not a window, so we can't emit more radiation by heating up as efficiently as we would like. And what gets in the way is the vapor. And here what we see is the vapor. And the vapor depends exponentially on temperature. So at a fixed relative humidity, it says the saturation vapor pressure depends on temperature, and the actual vapor pressure, the amount of water vapor in the atmosphere, here measured by partial pressure, decreases with height. And the funny thing about the vapor is that if we imagine this is a situation with the solid lines here, that there's an amount of vapor that's controlled by temperature, which is decreasing with height. What happens when we increase the temperature? Well, when we increase the temperature, then we get more vapor because the relative humidity is staying constant. And we have more vapor and we get this line. Well, then we ask ourselves, well, how deep do we have to go? We're coming from space, so we're diving into the atmosphere. How far do we have to go before there's enough vapor to emit, to be responsible for the emission that we see? In a cold atmosphere, we have to come down to here, which is at this temperature. In a warmer atmosphere, the amount of vapor increases, and so we don't have to go as far. And it turns out how far we have to go, because vapor is determined by temperature, is as far as we had to go before to be at the same temperature. So the funny thing about the vapor, the vapor parts of the atmosphere, is that they don't let that part of the atmosphere respond to warming. If you warm the atmosphere, you increase the vapor and the emission moves to a colder temperature. And the colder temperature is the temperature what it was before at the warmer temperature. So if you want to try to remember all that, you have to just remember is that the emission is partly coming from the surface through the window, partly coming from vapor, but vapor doesn't respond. The emission in the vapor bands isn't very sensitive to the surface temperature. Gases are something else, because gases we can vary independently of temperature. So here's an example here. If we have a given amount of CO2, let this thin line be 0 and the thick line be the given amount of CO2. We can say, well, how far do we have to get into the atmosphere before we have enough CO2 that we think of the emission of radiation coming from there? And I said we have to get this deep, kind of halfway through. And that's the temperature we're emitting at right over there. So that might be this guy, you know, it's kind of more towards the upper part of the atmosphere where it's cold, and we're getting emission from cold temperatures here. So what if we increase the amount of CO2? Let's double it. So if we double the amount of CO2, what we find is that we don't have to go nearly as deep into the atmosphere to get enough CO2, an optical depth that causes this emission to happen from that height. So with the gases, we can vary them independently of temperature, and we get emission at a colder temperature. So we can change the emission in the gaseous bands by varying the surface temperature, or by varying the amount of the gas. So here's the example: is if we have the gas and we just fix it, we can vary the temperature, the gas doesn't change, and now the emission's at a warmer temperature. Or we can keep the temperature fixed and vary the amount of the gas, and then the gas varies. So when you try to understand radiation in the atmosphere, how it gets out, you just have to realize these 3 different ways in which these photons escape. Some escape right through the window. Those are the nice ones. They respond to temperature. Some are controlled by gases. So varying the gases varies how they work. And others are controlled by vapor. And the more the vapor plays a role, the less we get from the window, and the less we're able to use surface temperature as a regulator. So it's kind of like, in a way, if the vapor gets more and more, it's like Obelix's getting so fat that he just doesn't exercise anymore, stops carrying stones, and he has no way to respond to his extra energy. So that's the radiated energy transfer. That's how we understand it. We can calculate it with great precision. So what does that do for us? Oops, what it does for us is it tells us how to calculate the radiation, but to do that, we need to know something about the temperature. And this is the second part of the deep dive. In Earth's atmosphere, the weather layer, where we have weather and storms, is controlled by the fact that there's water vapor as a greenhouse gas causing the atmosphere to cool. And if it was left to cool the atmosphere of its own devices, that cooling of the atmosphere leads to radiation that goes to space, and that vapor sends radiation which goes to the surface. So the cooling of the atmosphere warms the surface and loses radiation to space. So when we try to figure out Earth's energy budget, we don't just have to figure out how to balance the surface at the temperature at the surface. We also have to balance the atmospheric energy budget. And if we tried to let radiation do that all by itself, we would end up with a temperature profile which is gravitationally unstable. We would end up with effectively colder air above warmer air. And what that does is it causes the air currents to swirl. And so you get this convective instability. That's weather. And it's the air just kind of mixing through the troposphere. And that's happening because the atmosphere is a greenhouse atmosphere. It's losing energy to the surface and warming the surface, and to space to balance what's coming in from the sun. And in order for the temperature profile to come into equilibrium just through radiation alone, it would adopt a vertical profile, which we can calculate, which is unstable. So what happens is these storms develop and they warm the atmosphere. But then you get this sort of tug of war between radiation trying to cool the atmosphere and storms trying to warm it. And the storms warm it because they bring up moist air from the surface that's evaporated from the surface, condense the water. That latent heat or vaporization enthalpy is left in the atmosphere that's warming the atmosphere, and it falls down as rain. So the way rain forms in the atmosphere is an important part of the energy budget. And what most people don't realize is that we have rain because of the greenhouse effect. The greenhouse effect is cooling the atmosphere, and that's creating a need for convective heat transport into the atmospheric interior to balance the radiative cooling. So I don't expect you to have followed all of that, but if you were able to kind of keep up roughly, I hope you would just believe that there's some fairly simple arguments that have something to do with radiation and convection, which explains how we think of the atmosphere as a column and how we think about its energy exchange. We can put those ideas into a fairly simple model, which calculates layer by layer how the radiation works in enormous detail. And it imposes that rule about how the convection works to maintain a certain sort of stratification. And we can then calculate what would happen if we increase the amount of CO2 by a factor of 2. And that's what we've done here. These are old calculations that go back nearly, well, more than 50 years. And we've gotten better and better at doing the radiation, but the calculations haven't really changed. And they show what we call the climate sensitivity. It's the change in the surface temperature for doubling of CO2. And what you see, we get numbers between sort of 2 and 3, and they depend on the surface temperature. What's happening here is as we increase the surface temperature, the window gets a bit smaller. And so our ability to cool the surface is a bit reduced. So we have to warm the surface a bit more to match a doubling in CO2. And so the amount of warming you get by doubling CO2 in a warm planet is a bit more than in a cooler planet. But it's roughly linear. You could fit a pretty good straight line to that. The other thing you could look at is the relative humidity, because that window is from the vapor, and the vapor sort of blurs the window. And it turns out for most values of relative humidity, the response is also pretty linear. A more humid atmosphere is less effective in responding to a radiative forcing from CO2. But the dependence isn't really a complicated thing. It doesn't look like those curves with the whole bunches. We take all of those ups and downs of the absorption features, and we see a pretty simple response that if we double the amount of CO2, we can balance that by warming the atmosphere by 2 to 3 degrees, depending on what the temperature is, what the humidity is. The beautiful thing here, and the important thing is that these curves are fairly linear, which says that this is how we calculate it in one point of the atmosphere. But of course, the atmosphere varies. Over here, there's a different humidity, and over there is a different humidity. We saw it swirling around. The temperatures are very different. The poles are very colder than the equator. But the fact that it's linear means that the average response from all of those differences is the same as if we had done the calculation using the average temperature and the average humidity. And so you can think about the system very simply is how would an atmosphere with the average humidity and the average temperature respond? And you can get a pretty good estimate of how the complex system will respond. That's the hypothesis that was put out in the 60s. And you could say we spent a lot of our time since then trying to figure out how this could be wrong. But this is the idea. It's something you could almost calculate by hand in the end. And it comes up with this sort of temperature response, and it says it's linear. And you say, well, that's too simple. It's a pretty complicated place. This is showing this window and how basically what I was showing here was how it begins to be nonlinear as this window here begins filling up from the water vapor bands. But for the most part here, it behaves fairly simply. And that summarizes a few points, but I want to go on to how we look at this in a more complicated way. And that's what we've done is we've built circulation models. And we started doing this when computers got to be a decent size in the early 1970s. And what we realized we could do is we could use the fact that the atmosphere is so thin that we could represent with a fairly coarse-grained representation of the Earth system. This is an early era model on the left and a late era model on the right. We could represent roughly how storms move energy from the equator to the pole, temperature differences between the pole and the equator, land and ocean, sort of a bit of the dynamics of the swirling motions of the atmosphere to kind of break ourselves free of some of the assumptions we made in that simple model. And the big ones we wanted to free ourselves from was what controls the pole to temperature heat transport, or the equator to pole heat transport. How water vapor is moved through the system. Remember that gray picture I showed before where we saw these very black areas and these very white areas? This sort of mimics that a bit. So we're kind of capturing some of that dynamics. And see if that really mattered. The theory said it shouldn't matter, but the theory didn't really say anything about clouds. And it left open the possibility that this assumption that the relative humidity was more or less constant wouldn't really work out. So we try to free ourselves of those assumptions. And we made a bunch of these models, and we increased them in resolution over the years as computers got faster. And what we found was that nothing really changed from that basic answer. Before we said it was like 2 to 4. We found out a few things. That the first answer would have told us that the poles would have warmed the least. But we show, because of the detail of the temperature structure and because of the ice melting and because of how heat's transported from the equator, actually we expect the poles to warm the most. And we could give another talk on that. We expect land to warm more for reasons we also can explain. And we can estimate some of these additional factors to say, well, the warming we got from that simple model probably is an underestimate, so it's probably a bit more than 2.5. And we also saw that clouds can change things quite a bit, but not in a convincing way. Sometimes it makes it worse, sometimes it makes it better, but we didn't really, out of these models, come up with a convincing idea about how clouds might respond to warming. So that's what I said. What has it taught us? It teaches us that there's proportionally, let me move that, proportionally more warming to be expected towards poles and over land. The retreating snow and ice amplify the warming. There's not much signal of cloud changes. And the models, these more complex models, are consistent with fairly simplified arguments about the hydrological cycle, which I'll come to in a second. So the things that we've learned, what I'd like to emphasize here, we didn't learn them because the models are so complex. We basically learned that the models didn't give us a reason to rethink our hypotheses that we developed in a much easier way based on much simpler ideas. So you could say we had a theory. The models allowed us to calculate what would happen if we relaxed some of our assumptions. Are there surprises? We didn't find any. And we also had 40 years now of observations from this big global experiment to see if it's consistent with the simple ideas. And all of these things line up, so we have simple ideas which work. We have more complicated models which relax some of the assumptions that still fits the picture. And we have observations which also fit the picture that we would have developed 40 or 50 years ago. So we're pretty confident about how the Earth responds to more CO2. Kind of like we'd be, pretty confident how Obelix would respond to eating more wild boars. He'd get fatter and the Earth would get warmer. So let's come up from that dive. We'll come up for some air here. And I'll just try to reiterate some points. So if you blanked out for now, or if you wanted to scroll forward to this time point, the up for air is that we understand pretty well the radiant energy transfer in Earth's greenhouse atmosphere. The response to warming, how radiation responds to warming, is pretty linear. So the expected change that we get from CO2 more or less depends on the global mean climate. Models that allow variability and 40 years of data kind of support this understanding. And I'd say quantitatively, this tells us a few things. The warming should be about 2.5 to 4 degrees per doubling of CO2. We can say a bit more about where the warming occurs and what this means for the hydrological cycle, which we'll come to. And we probably can estimate to within say you, for whatever reason, you decide you don't want the temperature globally to rise more than a certain number, 2 degrees, a lot of people say. We can tell you within a factor of 2 about how much carbon you could emit. It's a lot of carbon, a factor of 2, so we'd like to do that better, but that's what we can do. So Earth's warming, it's because of CO2. We know that, we've done that. Now what? I mean, what's left to do? You could say, well, we'd like to know better how much carbon we can really emit for a given temperature target. But I'd say there's actually maybe even bigger questions, because we know the Earth's going to warm, and we want to know what that means. It's not a lot to, what does it really mean if the Earth's 2 degrees warmer? It means that it's 2 degrees warmer. But all these things are happening. They've always happened, maybe, or maybe not. So when we look at, this is just some examples from the summer. We just in Germany had these big floods. I mean, they're fantastic's the wrong word, but it sounds positive, but they were spectacular, catastrophic floods in the Rhineland. In Jiangsu in China, there's even bigger floods. The US audience might remember these Western Canadian heat wave, or they might know it as the Northwestern heat wave. Portland that just had these skyrocketing temperatures. And I don't know if people are following these days, there's been huge fires in Sardinia. There's Siberian fires that people are talking about. So what's up with that? Is that bad luck? I mean, something terrible is happening somewhere all the time. So maybe we're just learning about it more often. So, or maybe it's just a bad year. Bad things happen. Really bad things happen once in a while. Or maybe it's bad management, and bad management could be different things. It could be bad management because we're putting so much CO2 in the atmosphere, and the atmosphere is warming. So this is because of climate change. But there's other forms of bad management, is that we just build infrastructure in places that we didn't know were vulnerable. We're going to, even with the old climate, there's going to be places where strange things happen once in a while, and we might not have known it, and we build infrastructure there, and then something strange happens. So that's another form of bad management, where we're building infrastructure in places which are vulnerable even with the given climate. These are things that I think as a scientist, we'd like to be able to say something about. Are events like this happening because the world is warming? Is it happening because we put infrastructure in vulnerable places? Or is it just, bad luck? So the problem is that if with warming, the weather is changing, there's two ways in which it can change. It can change its tone, or it could change its tune. And we have a handle on how the tone of the weather will change with warming, but not the tune. So let me explain those two things. Here's the tone. It's really what we talk about. You hear it all the time. People talk about, oh, the Earth's warming and we're going to have more droughts and more floods. And to a normal person, that might sound a bit weird. They think they get everything. These climate scientists, they have warming, and they can get more droughts and more floods. So they can explain everything. They can explain more blizzards and more heat waves. So what's not to explain with global warming? Well, the argument with the floods is pretty simple. You can think of the atmosphere as a bucket for water. And normally what's happening on a nice day is that water is being evaporated from the surface, and it will keep evaporating from the surface until the bucket is full. Or in unsettled weather, the bucket's kind of lifted up and tipped over, and it's raining from the air. So if that's the way the atmosphere works, it either collects water that's evaporated from the surface, or it tips it back down onto the surface because of the weather conditions. Then the size of the bucket really matters. And it turns out that the size of the bucket is an exponential function of temperature. So the atmosphere's capacity to manage water or to hold water depends exponentially on temperature. That's called the Clausius-Clapeyron equation. And it means that in situations where we're evaporating water, a much bigger bucket can suck a lot more water out of the surface, or much more quickly, because the difference between how much the bucket wants and how much it gets is available to it is much bigger. And so it's very effective in situations which are drying out the atmosphere very rapidly. And then if you turn the bucket over, then you get it back again, and you get a lot more water out of that bucket than you get out of this bucket. And these I drew roughly to scale from the difference between kind of a warm tropical atmosphere and a kind of a winterish mid-latitude atmosphere, not a polar atmosphere by any means, but you see a big difference. That's why summer rains are much more torrential. Flooding, big flooding is a summer thing. It's not a winter thing. And that's the bucket turning over. Drought too, if you're going to dry out the landscape, that's going to happen a lot more in the summer. So we know that. So if you warm the planet, you're making the bucket bigger, and you're increasing both the drying and the moistening extremes in general. It doesn't tell you if that's going to happen in Canada or somewhere else, but in general, this is changing the tone. It's making the music of weather louder. So we expect that to happen. So were the things we saw just that change in tone, or were they a change in tune? And what's a change in tune? The change in tune is the circulation, and the circulation in the atmosphere is fascinating because it couples scales spatially and spectrally. So it spatially means it connects places like the Western Pacific to the eastern seaboard of the United States through large-scale planetary wave-like ripples in the atmosphere. Whereas when you have more rain here, it causes a ripple that goes through the whole atmosphere and changes the weather patterns over Florida. That would be this sort of remote effect. But there's also a spectral effect that the scales here, this is a blow up of the cold air that came in. This is from MIT, and it was explaining this cold burst of air that they had last winter or 2 winters ago, I forget. And what you see is on these large scales, highs and lows, this pattern, these large scale ripples, you have lots of little ripples, and these little ripples are individual storms. And the little ripples might also be the storms which are responsible for the heavy rains here. So the little whirls or the little ripples make big ripples, and the big ripples kind of fold on themselves and make little ripples. And all of these things are interacting through the laws of fluid dynamics in ways that give rise to the local weather. And the local weather matters. Here's the example of the German floods. It's just a radar loop. And the floods were over here near Luxembourg. There's Frankfurt. Many Americans are familiar with Heidelberg, which is out here. And this is the Rhine Valley going along here. And here it's raining in the bright colors now. It's raining. It's raining over there too. If anything, over here, it's raining more intensely. But the big floods happened over here. And what happened if you come back here to the period of the heavy rains for about a day is that if you look at this pattern, you see it's just sort of swirling with the center of the swirl around Erfurt in the middle of Germany. And what made this weather pattern particularly potent, and what we see with a lot of extreme weather, wasn't really the tone, it was the fact that it lingered. So normally when we have these lows, like the lows drawn in this map, they're carried by these large scale currents and they just kind of move through. So you have bad weather for a day. What happened here is we had bad weather for much longer than a day, and it just rained and rained and rained and rained and rained. So the persistence of these little whirls has a huge effect on extreme weather. And this is what I would call weather's changing its tune. And so a lot of people talk about this, the wavy jet and stationary features. And scientifically, we really don't have much idea if weather is changing its tune with warming. But if it does, it can have a huge effect on extremes. And the problem is our models, which we did develop to look at this global picture, to kind of stir around things, to get an idea of the difference between the continents and the oceans, the poles and the equator. They're pretty good for getting the tone. They're pretty good for kind of testing ideas about how sensitive the very simple calculations are. But they don't at all capture the range of scales we need to get the tune right. The way things work in these, what seem like complicated models, and people who use them still talk about how sophisticated and complicated they are. But the assumptions they make about how the atmosphere exchanges heat in the vertical are still the very simple rules of thumb that we used in the very simple one-dimensional models that I showed you the calculations of in the beginning. So getting the rain right, and it gets the right the amount of rain right, and geographically it tells you it's raining in the tropics and in the jet streams, but any specific locality, getting the rain over the Amazon or the Congo, getting the monsoon, having the rain in the right part of the West Pacific to cause these large-scale ripples, that's things that they weren't really designed to do, and they don't do very well. And on top of that, even if it got the rain right, it wouldn't get the interaction with the local landscape, which is what's responsible in the end. If it rains a lot over the ocean, you wouldn't really call that an extreme weather event. The fish might, enjoy all the fresh water, but it's not going to cause a town to flood away. So this interaction with infrastructure, you need scales which we just don't have in these sort of models. And that's where the future is sort of exciting, because in the very beginning, when we made these sorts of models, I said it was possible to make them on early computers because the atmosphere was thin. And this allowed you to approximate it as sort of thin layers that kind of moved around in 2D with simple rules to manage the vertical exchange. If we want to do better and really capture the weather, the overturning of the atmosphere, we need models that aren't able to represent scales which are measured by the distance from the pole to the equator, but they're able to measure scales which are measured by the thickness of the atmosphere. So the thinness becomes a problem. And if you do the calculation, you figure out that to represent the storms, the weather in the atmosphere, you need about a factor of 7, 2 to the 7 in scale, about a factor of 100. Reduce the scale by 100. So instead of 1,000 kilometers, you need 10 kilometer scales we're talking about. And 100 is about 2 to the 7. And if you increase the resolution by 2 to the 7, there's 4 dimensions, it becomes 2 to the 28. You need 2 to the 28 times more computing. So it's a ton more computing you need compared to the early models in the 70s, 2 to the 28. But computers have been growing exponentially as well over the years. And a doubling happens every year and a half in computing power over the past 50 years. And if you say you want 28 doublings, how long do you have to wait if every doubling takes a year and a half? You have to wait 42 years. And if you think we started this in the 70s, 42 is a magic number. It means about now we should be able to represent scales where we can capture the weather. So this is what we're doing. And here's an example of a calculation we did recently, which I'll let it play again. Let's see if I can. So here's an example of a calculation we did recently, which, there it goes. So this is just an Earth at night picture that we superimpose at night just to give you a sense of the day. But as the day comes around, what you'll see is the weather. I mean, it's a simulation. It's a simulation at 2.5 kilometers over a global grid that we can run, for months to years on filling up our computer. But it's giving us a whole new capacity to look at how climate and weather interact. And this guy, you get to wait through the night here and see it again. You can see that hurricane that was sort of developing off the coast again the next morning. It's gotten worse or better. But it shows you the power of what we can do with a new class of models, which don't represent the atmosphere as multiple two-dimensional layers connected by a statistical rule of thumb, but actually simulate the weather along with the climate. We're coupling these models. This is the day going now fast. And what I'm showing is how we can couple these models with an ocean. And we'll see the richness. Mostly I talked about the atmosphere, but you see the Gulf Stream up here off the east coast of North America. You can see how that's evolving. We put on the near surface winds to see how all of these pieces come together like a symphony to create our climate system, and how it embodies so many differences of scale. As we move through here, we can see the clouds emerging at yet a different scale. If I draw it a bit forward, a bit more fast, we can see the ocean eddies here. So you see these little rings and eddies and folds which get shot across the Atlantic here. The Gulf Stream with its ring, the ring currents here, which people talk about in hurricane season in Florida. So you can put all of these pieces together and simulate the way weather and climate interact to maybe get a glimpse into what the future of a warmer world holds in terms of how the weather will change. So I'm going to jump ahead because I'm talking long and say we could do that today on a machine like this that exists in Japan. It's called Fugaku. The calculations I showed were done on a machine 2 buildings over from me, which is a modest sized machine, but it's 300 times smaller than this machine. So if we had that machine, we could do calculations like I was showing at a finer scale for decades, again and again and again. We could really begin exploring. We would create a microscope which would allow us to explore future weather. But it's expensive. To have a machine like this, we need people who would work on it. So we're really talking about, if we would want to get a glimpse into future weather, we're talking about an investment of 200 million a year and a facility that looks like this, dedicated to trying to understand how weather will change with warming. So the real question is it worth it? I think it'd be fascinating, but I guess in the end, it's people like the ones listening who have to decide. Let me just leave it with this. The knowledge base is there to tell us roughly that the world's going to warm with more carbon, and roughly how much carbon we can put in. And we can give you some rough ideas about what that will mean regionally. We really can't tell you what the difference is between a 1.5 degree warmer world or a 2 degree warmer world. And we can't really say with any specificity what a 2-degree warmer world actually means for infrastructure, for adaptation, for ecology. In principle, we could, though. The technology and the know-how, and we're developing that here, exists to do better on both counts and create new types of information systems. And these are 2 articles talking about that. And a number of us can't really fathom why we're not doing that. Because if we're contemplating the types of investments that we are contemplating to adapt to warming, which will happen, why aren't we doing our utmost to try to understand what that warming actually means for weather in a warmer world? So with that, I thank you very much for your attention, and back to you, David.
Bjorn, thank you so much. That was absolutely terrific. And I must say, you know, when I think of climate change, you know, I think about the Earth warming up and so on and so forth. But I never thought about actually being able to predict on the scale that you're talking about what the weather will be looking like, you know, in all the different parts of the world. I mean, that's almost unfathomable to me that we have that within our capacity to be able to get that kind of temporal and spatial resolution on basically, correct me if I'm wrong, but aren't you saying that our weather forecasts could really be much more accurate if we were to invest the resources in this kind of computer modeling?
It'd be a different kind of weather forecast. So what we couldn't say, what we couldn't say is that, you know, on Tuesday in 2080, in the first Tuesday of November, it's going to rain. I mean, that sort of thing we couldn't say at all. But what we could say is what would be the typical weather that we would experience in a warmer world. So we wouldn't, normally what happens when you think of climate, you say climate is the expected weather, but when we predict the climate, we're predicting more or less the expectation values. We're not predicting the things that go into that, the events. So the idea is that we could predict reasonable, plausible, reliable distribution of events, which then make the climate. And this would allow you to investigate things like vulnerability. You say, I'm going to build a factory in this valley. What would we expect for a 100-year flood? We wouldn't tell you if it will come this summer or next summer, but we would hope to be able to say that you should expect 100-year floods that look like this. And this is how they'll change in a warmer climate. And that's what, so that when I say predicting the weather of a warmer world, it's not, we won't get the phase right. So we won't tell you on what day that weather comes because that's chaotic and we won't do that. But we should be able to predict reliable distributions of events and how those distributions will shift with warming in ways that we can't do now. So I don't know if that distinction is clear.
No, I think it's important to make that distinction. But it seems to me that this using the data in this way, you'd be in a way to say, here are areas that could be vulnerable to, so for example, the wildfires that we're having in the US and the floods that have happened in China and Germany and so on and so forth. You can't specify the day.
Right.
But you can say, given what we know, these are areas that are at risk. And I guess I'm wondering, you know, thinking about the fires that we've been having here and whatnot, is there a way in these models to be talking about how, you know, that event or those events then can, you know, interact with climate change and this sort of, how do I say, positive feedback cycle? And it seems like models would be a great way to get at that as well.
Well, that's exactly it. If people read the newspapers, they're rife with sort of climate speculation, I would say. It's sort of informed, semi-informed, modeling where people basically are just speculating about all the things that could happen. They say, well, if we have warming, then the ice sheets collapse, and the ice sheet collapse cause the weather patterns to shift, and the weather patterns shift cause the Amazon to, dry out, and then that goes and puts more carbon, and they come up with these cascades, but they're just sort of, they're
Arm
speculation.
waving.
It's sort of science fiction. There's a scientific basis to some of the arguments, but it's speculation, and this allows us to really work through these ideas in a scientific way. Yeah, and it would help us understand if there are surprises or vulnerabilities that we don't know about, because the reality is that we are doing an experiment, and when you experiment with a system like this, it's the same thing. Right now, depending when people watch this, hopefully the COVID thing will be long over, but this is also an experiment in virology. I mean, the way we're growing new virus variants through, our social behavior and making things much worse, because, now we're just basically farming all sorts of variants of the virus to kind of send around. So we're going to be doing this experiment. We'd kind of like to be able to work through what the scenarios might be if we want to use a science-based planning. So.
Yeah, and I think the important thing to communicate is, what science has achieved. I mean, and you did a good job of that, in the beginning, saying how much we have really learned about global warming, climate change, et cetera. But also acknowledging that there are new things we're learning, right?
Yeah.
And I just to throw this out there, with the modeling you've been doing and whatnot, have there been any things that surprised you? Did you notice something that you hadn't really thought about before, in terms of what the modeling was showing you? Because I think it's important for people to understand.
Yeah,
it's not,
what I'm
yeah,
learning, it's sort
yeah,
of is the old models that we had were kind of highly adapted, if you would phrase it nicely, to what we know about the system. And when we run the new models, we kind of let them loose. And what we notice is many sort of things that were polished over, which caused the system to behave in how should I say it, in blatantly wrong ways. But they're just errors, bugs, in the code. And what we're seeing in the present generation model is the sensitivity to vertical mixing, and what ended up being bad assumptions. In one of our old models, which we had for a long time, we had a bug which made when the wind blew that way on the ocean felt it if it was going the wrong way. There's just a sign error. But it was sort of, we had such a long time step, and it couldn't really do its thing. And when we coupled the model on these scales, the ocean becomes much more responsive to the atmosphere, and suddenly everything was out of whack. And we noticed, oh, we had this mistake, and it just didn't do anything in the old model. So it's showing me sort of physical vulnerabilities in how the system works together, in very interesting ways. And right now we're just trying to put it together so we can run it for, we're doing these preliminary runs for a year, and we're getting, the first results. But yeah. So for me, I'm really excited because I want to look in the microscope, and we're just tuning it right now. So it hasn't. I'd say it's still too early to say it's sort of changed my view on the climate system, and it could be. A skeptic might say, we'll do this, we'll spend all the money, we'll use the computers, and in the end, maybe we don't see anything different. Wouldn't be so bad. I mean, it'd be kind of boring for me as a scientist, but for society, just kind of like when we built those old models, in the end, you could say, well, they didn't teach us that much compared to the 1D model that you could do by hand. But in the end, that was reassuring because it told us that we weren't off track. So if we do see surprises, we'll see fascinating features and structures. We'll be able to quantify things. We'll link to many parts of society much better. They'll be very useful. Will it change the way we understand the climate system? I don't know. But that's the big unknown. That's what we want to know. So.
Yeah, no, and I would rephrase that. That's what we need to know.
Yeah.
I mean, I think that's absolutely critical. I guess the other thing that I wonder about is how do we communicate this to the public? And one way of doing it is what we're doing here right now. But we also have to communicate it to the government. And I do see this as an international problem, right? We need to
Yeah.
be working together to really get a handle on this. And I'm wondering if you have a clear picture of what we could do to have, a much more, international collective effort to get a better handle on climate change.
Yeah. So we do. A number of us have been proposing, and there's a paper that I cited at the end in the Royal Society, a briefing, which is going into this year's climate negotiations. It's really just making the case that to do to attack the problem in the right way, we need a scale of computing that really requires international cooperation. And it's not something that you would want to do. It would be even not responsible to do this in every country because the energy resources are enormous. So there's a real advantage of working together to make the machines and to make the models that would run on those machines work efficiently, which then could serve the many different applications, whether it's water management or it's scientific inquiry. In one way, these simulations work like accelerators. So scientists will then look at how they behave, but also people, the information they produce will be informative for food security, finance, reassurance, water management. And so you really would like to do this as a cooperative effort. And right now, the thing I find kind of funny with the science is the science is being used by the policy community to argue that the world needs to cooperate to achieve emissions targets. Okay, that's a reasonable policy wish. And it's demanding a sort of global cooperation that we're struggling to do. And it's supported by the scientific community, myself included. But if you look at the level of scientific cooperation to work on this problem, it's actually pretty meager. We all agree to coordinate. There's lots of coordination. So the science is coordinated up and down, but coordination is different. Coordination is let's all do our own thing and talk about it and standardize our output. Cooperation is really working on something together. And that's what the problem, in my mind, needs. It doesn't mean everyone has to work at this center, but there's really a role for this scale of science to deal with this scale of problem. And I think it would empower scientific inquiry up and down the hierarchy in the sense. A lot of people like to pose small investigator-based science against big science. You need both. I mean, science needs the quirky thinkers who are really doing their own thing, but it also needs big microscopes or big telescopes or big computers. And I think we're just not ambitious enough on the one end of what we could do together.
I agree, and I hope that what you are doing, and again, I'm really impressed with not only the science, but the way in which you're trying to make it clear to the public, what we really need to be doing. I mean, yes, the space race, that was terrific. That got us, amazing places. But if we could bring that same collective and cooperation to climate change, the world would be far, far better off. And again, I appreciate all that you are doing to try and make that happen. And Bjorn, at this point, I think I need to say goodbye, but really, really appreciate you being with us today.
Thanks very much for having me, David, and good evening to you.
Thanks for watching Curiosity Meets Discovery, research talks from inside the Max Planck Society. Visit mpfi.org to sign up for updates. Follow us on social media at MPF Neuro. Curiosity Meets Discovery was produced by the Max Planck Florida Institute for Neuroscience.